So let's take some time and look at the TCP protocol. TCP, or the Transmission Control Protocol, is a connection-oriented transport layer protocol. So let's break that down. What does connection-oriented mean? Well, essentially, its utmost responsibility is to ensure the guaranteed delivery of data, and it does that through a three-way handshake. It actually establishes a session with the other computer. It reaches out and says, hey, I want to talk to you. Let's establish a session. And if there's no security tools or there's no network restrictions or access control lists that are blocking those packets from making it to the other system, that other system will respond and acknowledge that synchronization attempt. So these computers go through synchronizing their communications so that they can handle errors if packets become corrupt in transit. And TCP uses that by using acknowledgement and sequence numbers in the TCP header. So one way we can think of TCP is it's the equivalent of going to your nearest FedEx or UPS office and paying to ship a package, but we're putting signed on delivery, we're putting tracking, and we might put insurance on it, right? Like that package is going to get there, we're going to know it got there, we're going to have all of the evidence of the transaction being successful. That's what TCP essentially is doing. It's ensuring that the data gets to its intended recipient and it got there the way it was intended to be received, with integrity. So let's take a deeper dive in the TCP handshake. So again, this handshake utilizes synchronization or SYN flags and acknowledgement flags. So we see on the left we have a workstation client who wants to establish a connection to the web server. So this is again that client to server model, but we're now zooming in at the packet level to see generally what types of packets are being sent. So we can see the first communication, denoted by the first line at the top, has a TCP packet, and in the header it will have a SYN flag set with the value of 1. The web server, once receiving that packet, will send its own synchronization bit turned on, a flag turned on, with a value of 100. And it sends an acknowledgement of 2. So the way this synchronization and acknowledgement works is, anytime I want to acknowledgement receipt of another synchronization packet or packet that had a synchronization bit set, I will increment the value by 1. So my SYN1 packet becomes ACK2 because it said, I saw your SYN1 and I'm acknowledging the next number 2. That way the client knows that it in fact observed and saw the value of 1 set in the synchronization packet. So this incrementing way of adding a +1 value to every synchronization that is sent and received ensures that the sender and recipient know that the last packet they had sent had been acknowledged and received. The client then responds with an ACK101 because we're incrementing 1 value to the synchronization flag that was set from the web server. And once we go through those 3 steps, SYN, SYN-ACK, and ACK, the client can now start making its requests in the form of sending raw data. We don't have to worry about doing synchronization setup, but again, note that every data packet that's going from here on out will have an additional synchronization number. So it would be SYN3, SYN4, SYN5, and then from the server we'd expect to see ACK4, ACK5, ACK6 correspondingly to the number of synchronization flags we sent. So long story short, every time we send a piece of data, we put a number on it. Every time the server responds, it acknowledges the receipt of that number by adding +1. Because if the packet was lost in transit or was corrupt, the other receiving server couldn't respond to a 1-up number because it never received the packet. So what happens here is, what happens if the client sends a SYN1 and the web server sends an ACK1 back? It's essentially saying, I saw your packet, but something was wrong with it. Send SYN1 again, and the server will keep responding with a SYN1 until it successfully processes the packet, if the packet is not corrupt in some way, and then it'll begin doing its synchronization and acknowledgements on the incrementing level. So sometimes when our internet gets slow, or there's static on the line if you're using DSL, or a router goes down, or a computer crashes when we were communicating, we might lose some packets. And the synchronization and acknowledgement schema ensures that the recipient of that packet always responds with the last acknowledged packet they received. So if we know what the last packet they've received, we can then just keep playing the last packet until they get it, and then we can move on in our communication. So let's look at the TCP header. So first and foremost, remember that the TCP header is within the IP header, right? Encapsulation again. We have an IP header, we have that IP payload, and this TCP header is now in that IP packet payload. And the first bit in that header starts with the source port. This is where this traffic is coming from an application perspective. And we want to go to this destination port. I want to connect to this type of service over the internet. And then again, we have those sequence numbers and acknowledgement numbers. That is the main function of the TCP protocol, to manage sequence and state. So we use those two fields for those valued numbers. We then have the data offset. This describes the offset of the TCP header so that the receiving application knows where the payload data starts. It's like saying, hey, skip this header and just go right here if you want to start processing data. We then have a chunk of reserved bits that are simply reserved and not for use. And then we have control flags. These flags dictate how the packet will be used. So these control flags specify a synchronization header or an acknowledgement header. There's also reset if you want to reset the connection. And then we even have a fin flag to say we are finished with the session. And using a reset and fin, you do the exact same way we did SYN and SYN-ACK. We do a three-way handshake of reset, I want to end this session with you, and then the other host will reset and acknowledge, and then we will send a fin packet, and then it will fin and acknowledge. We're done with our session. So that's how you do setup and teardown of these transport layer sessions. We then have the window size. This is how a recipient of data, This is how a recipient in the communications chain can tell the sender in window size or blocks of bytes, remember 8 bits is a byte, of how much data it's willing to buffer. This is what TCP uses for flow control. It ensures that the sender or recipient can't send more data than the other can receive or manage at a time. So if one machine is getting overwhelmed or the link is getting saturated, it can reduce the window size so the sender sends less data in the TCP payload. Then we have the checksum field. This uses the cyclic redundancy check to evaluate the header for integrity. The sender sets the checksum value. It does a mathematical calculation on the header, and the results of that is a mathematical outcome that is included in the header. The recipient checks the checksum, and if it is calculated different than what's in the checksum field, the recipient knows that something's wrong with the header, something has changed, and this is where that acknowledgement process will come in. It won't increment the acknowledgement number, telling the other sender, hey, something was wrong with the header, I need you to resend it. And then last but not least, we have the urgent pointer. The urgent pointer value is the placement or offset of the last bit of urgent data that is being sent in this packet. And the urgent flag is set in the control flag section of the TCP header. So let's pivot really quickly and talk about UDP, or the user datagram protocol. One thing to note in how it's different than TCP is that UDP is connectionless. It is not concerned with establishing a session or guarantee of delivery of that data. It's just trying to get data from one point to another as fast as possible. And in doing so, it has less overhead. It has a much smaller header, and the protocol itself does not do all of that work of synchronization, SYN, SYN-ACK, ACK. It doesn't have any of those controls. It doesn't have flow control. It simply sends data as fast as it can. So we could almost think of UDP, if we go back to the TCP analogy of, you're getting that package, you're getting tracking and shipping and insurance, and it's going to get there, and you got to guarantee that it's going to get there. Well, UDP is the equivalent of just writing a postcard or a letter, throwing a stamp on it, and most often it's going to get there. It's going to get there 9 out of 10 times, but if your letter doesn't get there, it was lost in the mail. That's what UDP is. The vast majority of packets are going to get to their intended recipient, but some will be lost, and that's expected, and that's okay, because the protocol was designed for streaming media, voice over IP, and it's used in gaming. Whenever we need data with low latency, I need to get it out of the interface and onto the network to get to that server as fast as we can. We want to use UDP. However, things have changed. We are starting to see TCP and encryption used a lot more in what used to be traditionally UDP packets, because our networks are just getting that much faster. So, like in all computing standards and specifications, things that used to not be possible are now possible. So we're reusing protocols in new use cases because they now work as intended. We can now do TCP for streaming media, and the end user has no awareness if that was TCP or UDP. It just gets there, it plays, it's fast, and it doesn't buffer. That's just what users want when they're online. They want it to be fast and responsive. And if we can do that with a connection-oriented protocol, we just improve the quality and guarantee of data delivery. But if there is a degradation in the network, let's switch to UDP so we get most of the data there, and we're fine with a little bit of data loss. Let's look at the UDP header. It's considerably shorter than the TCP header, really not much to it. We have the source port and destination port for the communications. We have the length field, the overall length of the header and payload. And then we've got the checksum field that evaluates the other 3 header fields to make sure that they were sent with integrity. And beyond that, that's all that's in a UDP header to get that packet out the door. So you can see in comparison to TCP, we've really cut a lot of overhead and management out of the process just to get data where it needs to go. So ports and protocols in summary. Remember, ports are ranged between 0 to 65,535, and they have those 3 ranges well known. The well-known ranges help us identify known and expected services. They help us also identify the flow of communications, right? We can use a well-known port to know if this is going from the client to the server or from the server to the client. That registered port range, this is where private and public entities, businesses, everybody in between can go pay and register for a port to be associated or registered to their protocol or application that they want to use on the network. And last but not least, we have that ephemeral port range. Remember, this is primarily used by clients because it's not meant to be associated to any application for a long term. It's dynamic. It's expected to change. And going down and talking about TCP/IP, we use TCP and UDP within the TCP/IP protocol suite. And remember, TCP and UDP are transport layer protocols. The primary difference being is that TCP is connection-oriented and UDP is connection-less. We want to ensure data gets there, use TCP. If we're fine with losing a few packets, use UDP. And last but not least, TCP manages and builds sessions using that 3-way handshake, SYN, SYNAC, and ACK, to ensure that packets are sent and received appropriately with integrity and in order.